I am now going to ask Mr. John G. Lee, our Director of Research, for a short address. Mr. Lee is in charge of our research laboratories. He has a Bachelor of Science degree in Mechanical Engineering and a Master's degree in Aeronautical Engineering, both from MIT. He has been with United for 30 years. He is a member of the Society of Automotive Engineers, the American Institute of Aeronautics and Astronautics, the American Helicopter Society, the National Academy and Space Agency Committee on Aircraft Aerodynamics. He is a member of the Connecticut Research Advisory Committee and is chairman of the Board of Regents of the University of Hartford. John.
I would like to talk to you this morning about research in United Aircraft, and in particular about the United Aircraft Research Laboratories. These comprise the central research establishment supported by the corporation. They are located here in East Hartford, right across the field from this building. There are, of course, many kinds of research, and this research is conducted all over the company. Only a portion of it is conducted at the central laboratories. Each division, in fact, has its own research program. Over the years, however, the United Aircraft Research Laboratories have, I believe, been one of the major factors in the technical advance of the corporation. Their specialty has been research into those fields which are of value to more than one division of the company. They have earned the respect of the manufacturing divisions and have been consistently supported by management. These words, consistently supported, are of the greatest importance because managements which support research on an off-again, on-again basis, however the economic winds may blow, in fact get no research at all. We have had consistent and increasing support, the latest example of which is the major addition to the laboratories across the field, now nearing completion.
Historically, the Central Research Group was formed in 1929 under Hugh Chatfield. Many of you will remember Mr. Chatfield.
As secretary of this corporation, he assisted in conducting these annual meetings from this platform for many years. But in 1929, when he first had the research assignment, the company was small. There were but 3 people in the research group at that time, and one of those was a secretary. Today, there are nearly 1,000 of us, and we are engaged in so great a number of problems that it is difficult to know where to place the emphasis. During the intervening 34 years, the research laboratories have passed through 3 distinct stages, each appropriate to the apparent needs of the company at that time. In its earliest stage, when the scientific needs of the company were quite limited, the laboratories concentrated on establishing certain essential technical services.
That work is not what we would call research today. However, it was important, and I would like to elaborate. For example, in 1929, there was no patent department in the company, nor was there any flight test organization. Both of these essential services were originated in the Central Research Laboratory at that time, and within 10 years had achieved independence and, of course, are serving the company very capably today. In the 1930s, the Central Research Group established the company library. Starting out with a single shelf of books on Dick Malloy's desk, the library now comprises some 40,000 volumes and 90,000 reports. And to me, the most important figure is that every day it handles upwards of 900 requests for technical information. The library is still part of the research laboratories and will probably continue to be so because it serves all divisions of the company. I doubt if many of you have been in the library. In fact, I can practically prove this, for during most of its existence, the library has been so crowded that if a stockholder came in, an engineer would have to go out. Beginning next week, however, the library will be housed in new and really excellent quarters in the enlarged laboratory buildings across the field. I cannot overemphasize the importance of a good technical library to a company such as ours, which is so heavily involved in the new aspects of science and technology. Our library is one of the best. Also, in the early 1940s, the first of the laboratory's wind tunnels was completed. There are now 5 major tunnels, and some smaller ones, ranging in size from a few inches to 18 feet across the test section. One of these tunnels is capable of speeds up to 10 times the speed of sound. Shock tubes and other special equipment allow us to test at very much higher speeds for brief increments of time. Needless to say, these facilities serve the entire corporation and have remained as an integral part of the research laboratories. Even after 18 years, the big tunnel is still running 10 hours a day, 6 days a week. More important than the tunnels themselves are the men who know how to run them and who know how to interpret the results. And this, I would like to remind you, is true in every branch of engineering and research. Facilities, money, administration. These are the tools, absolutely essential. But the thing that counts is the men. The most recent technical service which the research laboratories have established is the computation laboratory. This complex is devoted entirely to engineering computation. It does not include accounting, which is done elsewhere. It contains 3 of the large digital computers, a mass of analog computers, and a considerable array of auxiliary equipment. It employs some 220 people, about half of whom are professional mathematicians. It operates 2 and sometimes 3 shifts a day. Most of the major computing work in the company is done here. The computation laboratory is connected by automatic data transmission systems with Pratt & Whitney's engineering department, with their Wilgoose laboratory, and their Florida test center. It is connected with Sikorsky and with the corporate systems center in Farmington, and other connections are under study. Some of these connections are so effective that they bring the vast array of computing machines literally into the laboratory of the people who use them, but in the remote location. In its second phase, the research laboratories became involved in applied research, that is, research with a specific product objective. This is a type of research that could generally have been done by the manufacturing divisions themselves, had they been able to spare the time and the engineers. However, this collaboration resulted in some rather important contributions. I'm covering these things in history a little bit because I think you would like to know what becomes of the money and effort that goes into research. For example, in 1944, the end of the war, the Pratt & Whitney division was at last free to enter the gas turbine field. It cast about for available men who had some understanding of this new field. The original group numbered 12 technical men. 6 of them came from the research laboratories. The laboratories had been studying gas turbines for several years, and it was no accident that the men were there. Similarly, when work began on nuclear power in the company, the research laboratories again had been studying this field and contributed in a major way to the original group of engineers and scientists. And this happened again when the present Corporate Systems Center was founded. Not only did the research laboratories supply engineers with a pertinent background in missile technology, but they originated and completely staffed the group which is now the Weather Systems Center. These are examples where a whole new technical area was opened up. The key point I'm trying to bring out is not that the great development was not done by the divisions. Of course it was. The point is that at the beginning, research played a critical part. There are some other cases which are less spectacular, but perhaps equally important, and I would like to mention only 2 of them. At the request of Pratt & Whitney, the research laboratories undertook the systematic testing of aerodynamics of compressor blades. More than 80,000 tests were run. The resulting data on the mathematical methods derived to go with it provide one of the essential engineering tools which has made possible the Pratt & Whitney jet and turbine engines. It is doubtful if a similar body of technical data exists anywhere. A second example is a current project now underway, which is a collaborative effort between the Sikorsky Division, the Norden Division, and the research laboratories. This is the development of the flight simulator for vertical takeoff machines. The result is a unique device which will permit Sikorsky engineers to design the control systems, key systems, and other essential elements of vertical takeoff machines of any type, not limited to helicopters, so that the resulting machine will have optimum flying characteristics. This machine, this device, can be flown in safety by engineers and pilots alike, and the results to date are extremely gratifying. Now, before I move on to the last or present phase of the research laboratories, I would like to digress a moment to point out some of the aspects of modern research. The knowledge which research brings is not all contained in reports. Much of it is contained in the minds of men. The ability to use the new knowledge, to evaluate, to pass judgment on the remaining uncertainties, these things are most difficult to transmit to paper. They are understood by the men who worked in the field, the men who have done the research. And this is why we transfer men from the research laboratories to the divisions and why it has proven so useful. It is a policy we follow whenever we can, with only the obvious reservations of not transferring men who do not want to go and of not depleting our staff below the critical point. Research and development are often confused. They are much alike, but it is quite important to distinguish between them. And this can best be done by comparing their objectives. The objective of research is knowledge. The objective of development is hardware. Research can be accomplished by tests of models, by simulators, by theories, and by apparatus so delicate as to invite mechanical failure. Development, on the other hand, requires full-scale operation and apparatus, run under actual conditions or conditions deliberately made more severe than normal. And what comes out must be something that always works. Pratt & Whitney's dependable engines are made dependable through development. They may contain certain parts, turbine blades for instance, formed of a material which is a product of research. Or they may embody aerodynamic design, which is an outgrowth of research. But the reason they run for thousands of hours between overhaul is because they have had long and costly development. I mention these things because research and development almost always appear together in the public press and in the government budgets. They appear as R&D, with the general implication that they are equal. They are of equal importance, but they are by no means of equal cost. Development usually costs about 10 times as much as the research on the same project, and sometimes 100 times. I can give you one example. In 1945, we made some tests in the research laboratories on burning hydrogen and oxygen at a simulated altitude of 90,000 feet. There was no great interest in this at the time, not amongst the military. It was the pre-Sputnik period. Later in 1956, we tried this again, and this time on a much more elaborate scale, and Pratt & Whitney was quick to pick it up. By now, the space race with Russia was on, and the government was much concerned. This work became the basis, the starting point from which Pratt & Whitney's RL-10 engine was developed. The point I wish to make is that the original research, which showed what you could do with oxygen and hydrogen, probably cost less than $100,000. The development of the RL-10 to a reliable rocket engine as it is today has cost many millions. So when you read of an R&D budget, it is well to remember that it is in much the same proportion as the proverbial horse and rabbit stew. One large development horse and one quite small research rabbit. Now let me return to the third and present phase, what I consider the mature phase of the research laboratories. We are now engaged in three major activities. About half of our effort still goes into the central technical services, the computation laboratory, the wind tunnels and the associated fluid flow equipment, and the library. About 1/4 of our effort goes into applied research,
sort of thing which I've been talking to you about this morning. And the remaining quarter goes into basic research. I think the term basic research is unfortunate. We prefer the term subject-oriented research because it describes so much better what we're doing and how it is we go about it. For example, we undertook research into the subject of plasma physics about 5 years ago. That is, the physics of electrically conducting gases. We were not after a specific application. We did not know what we were going to find. All that we knew was that the company's business was heavily involved in gases. Cold gases for Sikorsky, they call it air, but it is a cold gas. Hot combustible gases for Pratt & Whitney, freons and other refrigerant gases for Hamilton Standard, but none of us had any experience with the super-hot electrically conducting gases. So we found out all we could. We employed the most able consultants we could find. We began to build up a staff in the research laboratories of young physicists whose particular training and interest lay in plasma physics. We forced ourselves to the frontier of this, where our own experiments and our own theories were pushing out into new knowledge. In the course of this research, we came upon a new concept for a space engine, an electric propulsion engine, and we exhibited one such engine in this room a year ago. Our subject-oriented research had uncovered a specific application, so we divided our group into two, one continuing the basic research, and the other to pursue the new propulsive device, which of course is applied research. If this work continues to show promise, and I could only say that it might, then it is conceivable that Pratt & Whitney might have a new development project at their disposal of great potential interest. I think this illustrates how subject-oriented research leads into applied research, which in turn can lead into development and production. A point here. It is sometimes difficult for the scientifically trained, subject-oriented research man to talk understandingly to the practical development engineer. But both men can talk to the applied research man. He is the true middleman in this picture. It is for this reason that we plan to continue applied research in the research laboratories as well as in the divisions. It gives us a common ground, a method of exchanging practical working information. I might go on for some length describing our current subject-oriented basic research and its intriguing implications. But I would like to take the last few moments to touch on another point which is quite a different sort. And it is that even in this day of rapid change and competitive technology, good ideas can lie around unused for a decade. And I give you, for example, the method of steering rockets called thrust vector control, of which you just heard something. When a rocket has escaped from the atmosphere, the only way to change its path is to change the direction of the exhaust gas which is streaming out the back. The Germans, during the war, introduced little rudders into the hot gas stream, and they were very effective when they didn't burn out. But as rockets improved and gas temperatures increased, it became obvious that no material would stand up. And hence all sorts of mechanical gadgets of the most complex sort were dreamed up whereby the rocket engine could be mounted on a swivel and steered about in spite of the very large and bulky lines full of liquid oxygen and liquid hydrogen which were attached to it. At about that time, over 13 years ago now, Arthur Weatherby, who received the award this morning, hit on the original idea of injecting gas into the side of the exhaust nozzle. And this sets up a shockwave system which deflects the main nozzle stream without introducing any solid substance which can burn out. It worked from the start. Not too well, I might say, at first, but it worked. And we were all quite stirred up about this in the research laboratories. But the invention was before its time. We did not know then that we were in a space race. There was no space agency, and the military was still following the German lead. But another of the men, George Haussmann, who shared in this award, and by the way, he's an applied research man, he saw the possibilities and kept hammering away at the idea talked endlessly to government people, made additional inventions, wangled additional tests to improve the performance, and now after 13 years, this idea is being applied to solid propellant rockets by UTC on the West Coast and to liquid propellant rockets by Pratt & Whitney in Florida, and the controls worked out by Hamilton here in Windsor Locks. And it appears to be the only practical method of directing the thrust of large single-barrel rockets. In closing, it is well to remember that the two vital products of a research laboratory are knowledge and ideas. And as I said before and must repeat, knowledge isn't all in the reports and books. The most interesting and most recent hasn't got there yet. It is still in the minds of men. And important ideas are not as obvious now as they will appear to be in retrospect. And too often, they are hidden under some unimportant but more immediate problem. It takes imagination to find these things. And as Einstein reminds us, imagination is even more important than knowledge. For while knowledge is limited, imagination embraces the entire world. I thank you.